In this lesson, we're going to connect everything we've learned about bonding and geometry to a very important idea, polarity. Up to this point, we've talked about covalent bonds as shared pairs of electrons, but in reality, those electrons are not always shared equally. When there is a difference in electronegativity between the two bonded atoms, the bonding electrons are pulled toward the atom with the greater electronegativity. This unequal sharing, or polarization, of the electron density causes the bond to become polar. We'll then look at how molecular geometry determines whether the entire molecule is polar or if the bond polarity ends up canceling itself out. By the end of the lesson, you'll be able to analyze both bond polarity and molecular symmetry to decide whether a molecule is polar overall. So first I'm going to talk about different kinds of bonds that can be formed. So if you think about some of the Lewis structures we've drawn, we have molecules that just have single bonds present, and we also have molecules that have multiple bonds present, like double bonds or triple bonds. So they actually have names for these different types of bonding situations. So when you have two atomic orbitals, either hybridized or not, they come in and they overlap end-on, which is the only way they can form that bond initially. They're going to form a single sigma bond. So here are two hydrogen atomic orbitals, and we're going to let them overlap. And so there's our single bond, and that's a sigma bond. Just remember, the first bond you're going to form is a sigma bond. And then here we have the unhybridized hydrogen. Hydrogen doesn't really hybridize. And we have oxygen hybridized into an sp3 hybrid arrangement. And so we're going to allow the hydrogens to overlap, and they will form two sigma bonds. All right, so pi bonding is when you have multiple bonds. So the first bond we form is still going to be a sigma bond. So we're going to go ahead and let the ones in the middle, right here, overlap end on. And so there's our first sigma bond. Now we still have two unpaired electrons. We have one in this orbital that is in the plane of the screen, and we have another one over in this one. They can't twist around to overlap end-on like that first sigma bond did. So instead, they're going to have to overlap in a side-to-side fashion. So my artistic abilities aren't really up for this because now it looks like we got two bonds. We really only have one because we have one electron down here and one electron up in the top one. So I'm going to show it with the second stick. So the first stick that you make when you're drawing these Lewis structures is always going to be a sigma bond. You have to have a sigma bond before you can form a pi bond. Any additional bonds you form are going to be pi bonds. So here is nitrogen. Remember, nitrogen has a triple bond. So we're going to go ahead. There's our end-on overlap. So there's the sigma. And then we got a side-to-side in the plane of the screen. And that's our first pi. And then we have these two orbitals kind of going back behind the screen and coming out of the screen. Like I said, my art skills aren't up for this. And so they're going to overlap and make a second pi bond. So it's just nomenclature, more naming stuff. So the first bond you make is a sigma. Any additional ones are pi's. And when you're looking at these drawings, it doesn't matter which one you decide is a sigma. You could say the top one is the sigma, and the other two would be pi's. All right, now let's go on to what the main topic is, which is polar bonds. So if you have a difference in electronegativity, so remember electronegativity increases the closer you get to fluorine. So the closer you are to the upper right-hand corner, the more electronegativity is. That means the electrons are going to spend more time with near the atom that has the greater electronegativity. It's kind of like you have two people pulling on a rope, and the rope is going to be the electrons in the bond. So the one with the greater amount of pull is going to be being able to pull the electrons towards itself. That doesn't really happen. Okay, so here we actually have an example. So we have hydrogen fluoride. It has 2 electrons shown as the bonding pair. I left the lone pairs off. So if it was an even sharing between the two, the electrons would be shown like this, and we'd have a nice symmetric electron cloud. Because fluorine is a lot more electronegative than hydrogen is. Fluorine's Pauling electronegativity is like 3.8, 2.98, 4, somewhere in there, and hydrogen is more like 2. The electrons are going to spend more time over by the fluorine. And so this is going to give it a small negative charge. That's a permanent negative charge. This little delta just means that it's not quite -1. It's like maybe -0.6 or something like that. It just means it's a partial negative charge. And then the hydrogen is going to have the corresponding positive charge because the molecule is neutral overall. So because the electron cloud has been polarized, that means that this molecule is polar and bond is polar. All right, so here we have the same example again. So if we have a difference in electronegativity, it's a polar covalent bond. If they have the same electronegativity, it is a nonpolar covalent bond. And there are cutoffs for it. They say that if you have an electronegativity difference greater than 1.7, it's an ionic. And then I don't remember, I think the cutoff somewhere out is like 1 or 1.3 for polar covalent bond. We're going to simplify things and say if the elements are the same, or the same element on either side of the bond, it's going to be nonpolar. If the elements are different, it's going to be polar. So we look at this first one, we have F2, it's the same thing, so it's going to be nonpolar. HCl, they're different, so it's nonpolar. It's polar. BCl3, they're different, polar. Click. S8. S8 is one of the allotropes of sulfur. It looks like a little crown. So they're all the same though, so it's going to be nonpolar. H2O, polar. C60, the buckyball, they're all the same things though, so it's going to be nonpolar. SO2, they're different, so it is polar. And then boron mononitride would be polar. All right, so figuring out if a bond is polar or not, that's easy. So of course we can't just leave it alone. We've got to make it more difficult. So now we want to look at how to determine whether a molecule is polar or not. So thinking about water, hopefully you already know that it's polar. Both bonds in water are polar. And then if we didn't already know that it was polar, the way we could figure it out is just imagine that we have a mirror plane. And you're going to pass this mirror plane through the central atom, through the oxygen. And if you can find a way to arrange it so that it looks different on opposite sides of this mirror plane, then it's going to be a polar molecule. With this, it's really important to remember that water has a bent structure, so that's how you end up with the lone pairs on one side of the mirror and the hydrogens on the other side of the mirror. There is a kind of a shortcut that I usually tell my students, and that is if you have lone pairs on the central atom, they break the symmetry. So if you see a lone pair on the central atom, you don't have to worry about what the actual geometry is. You're going to know right away that it's polar. The molecule is polar. So let's look at another example. So carbon dioxide, valence electrons, we have a total of 16. Remember that we always have 4 bonds to carbon. So you end up with this structure. And so we pass our mirror plane. These are the 2 easiest directions to draw it. You could do it at an angle, but you would still end up with that it is completely symmetric. So because it is completely symmetric, even though the bonds are polar, those dipole moments cancel each other out, and we end up with a nonpolar molecule. This is why dry ice is solid CO2, and the reason why it sublimes straight from solid to gas is because it is nonpolar. It does not stick to itself very much. Water, on the other hand, because it's polar, yeah, you have these little positive and negative charges, and it sticks to itself a lot. So that's why I was saying in the previous two lessons, I think, that a molecule's polarity has a huge impact on its physical properties. All right, so now we're going to say these trigonal planar molecules are polar or nonpolar. So we look at this first, and I've left off the lone pairs. So we look at this first one. This molecule is completely symmetric. So if you put mirror planes through it, like that, we got one going, I'm going to draw it. That may be dangerous. So if you put a mirror plane like that, it looks the same on opposite sides. Just pretend it's a straight line. Like that, again, it's the same on both sides. And your third one is the same on both sides. You could do funny angles, but again, just simplify things as much. So BF3, because it's completely symmetric, is going to be nonpolar. So now we have HBF2, and so this one, that hydrogen, throws the polarity off right away. So if we do, imagine our mirror plane going like that, it looks different on opposite sides because we have a fluorine on one side and a hydrogen on the other. And then we look at the last example, BH3, again, something's going to be polar. Completely symmetric, so it is nonpolar. Then other examples, I have linear molecules, probably because I had the CO2 example. So if you look at carbon monoxide is one of the ones where carbon only has 3 bonds. So it's an exception as far as that goes. So we look at that and we have 2 atoms and it's polar. Then we got carbon dioxide. We already saw that it is nonpolar. And then whatever this is, SCO, it would be polar. All right, so I just have kind of a preview of a next unit when we start talking about intermolecular forces and how they relate to phase changes. So the boiling point of a substance is a measure of how much energy is needed in order to get it out of the liquid phase and up into the gas phase. It can either be affected by the mass of it, the molar mass, because I always tell my students, just imagine you're trying to throw bowling balls versus ping pong balls. The heavier it is, the more energy you need in order to get it up into the air. And you also have to be able to overcome any intermolecular forces. And the way I normally kind of abbreviate it, summarize it, I'm not sure, the analogy, that's what I want, is the molecular stickiness. So polar molecules are going to have a greater degree of stickiness to them than nonpolar molecules. So here I have some examples of a whole bunch of different polar molecules. And they actually, I'll give you the actual dipole moment, or yeah, I think that's what I called it, for the polar molecules. And that's just a number that shows you how polar it is. So we have water, it has a molar mass, it weighs 18 units, and has a boiling point of 100 degrees C. So it takes a lot of energy to get water into the gas phase. Here's HF, it weighs a little bit more, its boiling point is significantly lower. Then we have H2S, weighs even more. It's almost twice what water weighs and has a boiling point of minus 60 degrees C. We have HCl. It weighs a little bit more. It is twice as much. And now it's minus 85 degrees C for the boiling point. And then finally we get to SO2, which has a molar mass of 64, which is 3 times heavier than water. And we're finally coming back up. However, dipole moment. It is not so much because of the molar mass, how much it weighs, as it is the dipole moment, how polar it is. So H2O is the most polar example. Oh no, it's not. HF is more polar. So 1.8 versus 1.83 probably how they ended up being in the above zero. H2S, at minus 60 degrees Celsius, it's got a very weak dipole moment. HCl, starting to come back up, but you can tell that it's still got a really, really low boiling point, even though it weighs twice as much as water. And then SO2, 3 times as heavy as water, has a dipole moment getting close to it, but it's still a lot lower than the boiling point for water. So that tells you how big of an impact the polarity has on the properties. So looking at some more properties that are due to of water that are due to its polarity. So we have water has a really, really high surface tension. That's because the water molecules want to stick to each other a great deal. And at the surface, there's an uneven distribution of how much they want to stick to each other. So it makes it even stronger. Water has really high cohesive properties. That's where it likes to stick to itself. So if you have a droplet of water on something that's hydrophobic, like sheet protectors, for example, you get these nice little droplets, and the angle between the surface and the droplet gives you a way to measure how hydrophobic the surface is. And then we got adhesive properties, and this is how much it likes to stick to other things. And so spider silk is a polypeptide, which means it has lots of amino groups, which are polar, and lots of carboxylic acid groups, also polar. And so water just loves to stick to the spider silk. Whereas if you have something like a nonpolar polyester, yeah, it doesn't stick to it. So that's it for polar bonding. So we saw that we have sigma and pi bonds. Sigma bonds form from end-to-end overlap, and those are the first ones that form. And remember, sigma bonds are single bonds. And then pi bonds are from the side-to-side overlap. They're a little bit weaker than sigma bonds, and they're called pi bonds. So a bond is polar when you have an uneven distribution of the electronegativity of the elements that the electrons are being shared between. And when you go to try to figure out where the electrons are going to spend most of their time, remember fluorine is our benchmark for electronegativity. It is the most electronegative out of all of the elements. And then we got the reason why it's polar is because it polarizes the electron cloud, and it's permanent polarization, so you end up with a permanent positive end and a permanent negative end. And then whether a molecule is polar or not is dependent on both whether it has polar bonds and on its molecular geometry. That's where we want to draw those mirror planes and try to establish whether we have a symmetric shape. I'm going to write that on there because I think I left it off. So if it is, the structure is symmetric, completely symmetric, I don't know how many M's. Symmetric, then it's going to be nonpolar. And then if it's asymmetric, it's going to be polar. And remember, if you have a lone pair on the central atom, I'm just using X, that causes it to be polar because that lone pair breaks the symmetry. And yeah, symmetry matters. As I was just saying, you can have polar bonds, but because it is a symmetric molecule, you end up with a nonpolar molecule. So that's it for polar bonding. Next time, we're going to start talking about balancing reactions and identifying different reaction types. Thanks for listening.